In the final winter of the Second World War, while the Reich burned around them, two brothers sat bent over a drafting table in a requisitioned German factory. Outside, the sky was split open by Allied bombers running their methodical destruction from horizon to horizon. Inside, under cold fluorescent light, they were drawing something that no one in the world had ever built before. No propellers, no tail, no fuselage. Just a wing. One enormous, perfect, seamless wing. And somewhere in Washington, decades later, that drawing would look disturbingly, undeniably familiar. This is the story of the Horton Ho 229, the aircraft that should have been impossible, the aircraft that may have changed everything, and the aircraft that the American government quietly made sure you never heard about. By the autumn of 1944, the Luftwaffe was dying. It had not always been this way. 5 years earlier, German air power had been the most feared instrument of war on the planet. The Blitzkrieg over Poland, the decimation of France, the Battle of Britain, each campaign had announced German aviation as something categorically different from anything the world had seen. But war is a machine that eats its own superiority, and by late 1944, the machine had run out of fuel. Allied strategic bombing campaigns had systematically dismantled Germany's industrial capacity. Ball-bearing factories in Schweinfurt, synthetic oil refineries in Ploiești, aircraft production facilities scattered across the Reich, all of them on fire, all of them running behind schedule, all of them producing less and less with every month that passed. But the damage wasn't only industrial, it was human. The Luftwaffe had entered the war with the most experienced cadre of fighter pilots on Earth, men who had refined their craft over Spain, over Warsaw, over the Channel. By 1944, most of them were dead. The replacement pilots coming out of accelerated training programs were being sent into combat with fewer flying hours than their opponents had accumulated in a single month. They were being destroyed not by inferior technology, but by inexperience, fuel rationing, and the relentless mathematics of attrition. And then there was the fuel itself. Allied bombing of Romania's oil fields and Germany's synthetic refineries had created a crisis that commanders described in classified memos as existential. Aircraft were grounded not because they were broken, but because there was nothing to fill their tanks. Pilots trained on simulators. Squadrons sat immobile on frozen airfields, watching Allied fighter bombers sweep the skies overhead with impunity. It was in this climate of catastrophic desperation that Hermann Göring, the Reich Marshal of the Luftwaffe, a man whose grandiosity had long outpaced his judgment, issued what became known as the 3X1000 program. The demand was almost insane in its ambition. Germany needed an aircraft capable of reaching 1,000 kilometers per hour, carrying a bomb load of 1,000 kilograms, with a combat range of 1,000 kilometers. And it needed it immediately. To put those numbers in context, in 1944, no aircraft on Earth flew faster than approximately 750 kilometers per hour in level flight. The fastest Allied fighters, the P-51 Mustang, the Spitfire 14, were exceptional machines. And they still fell short of what Göring was demanding by a margin that looked, on paper, like fantasy. He was asking engineers to leap a technological generation in the middle of a war. He was asking for a miracle, and remarkably, two men thought they could deliver one. Reymar and Walter Horton were not typical German engineers. Most of the Luftwaffe's technical development was driven by Messerschmitt, Focke-Wulf, Heinkel industrial giants with thousands of employees, wind tunnels, test facilities, corporate hierarchies, and the institutional inertia that comes with all of those things. The Horton brothers were something else entirely. They were dreamers with slide rules, and they had been building gliders since they were teenagers. Their obsession was aerodynamic purity, and they had arrived, through years of experimentation, at a conclusion that seemed almost philosophically radical. The conventional aircraft was wrong. Not slightly wrong, fundamentally wrong. The fuselage, that long tube connecting cockpit to tail, was not the necessary center of the aircraft. It was dead weight, it was drag, it was compromise. And the vertical tail, the horizontal stabilizers, the whole complex empennage structure that every other aircraft on Earth used to maintain directional stability, those were engineering confessions. They were the solutions you reached when you had accepted limitations you should have been trying to eliminate. The Horton brothers refused those limitations. Their vision was a flying wing, an aircraft that was nothing but wing a single continuous surface that generated lift across its entire span, eliminating the parasitic drag of a fuselage and tail entirely. The aerodynamic logic was sound. When every square centimeter of an aircraft contributes to lift rather than just structure, you gain dramatic efficiency. You reduce drag at the source. You extract more performance from every liter of fuel. And with the jet age arriving in 1944, that efficiency could be combined with the raw thrust of turbojets to achieve something extraordinary. They had already built it, in successively more ambitious iterations throughout the late 1930s and early 1940s. The Horton brothers had constructed a series of flying wing gliders, the Ho-1 through the Ho-7, that proved their concept was not theoretical. The wing flew. And now, with Göring's impossible 3x1000 mandate arriving on their desk, Raymar Horton picked up his pencil and began drawing the Ho-229. But building an aircraft that should not, by the physics of every competing design philosophy, be able to fly, that was only the first problem. The physics of a flying wing are not intuitive. To understand why the Ho-229 was so radical, you need to understand what it was giving up and what it was gaining in return. In a conventional aircraft, the tail serves a critical function. It provides a stabilizing moment, a counterforce that prevents the aircraft from pitching uncontrollably. Without it, any turbulence, any shift in weight, any variation in throttle becomes a potential catastrophe. The aircraft wants to become unstable because the center of pressure and the center of gravity are in constant, subtle tension. A flying wing eliminates the tail. That means it also eliminates the mechanism that manages that tension. The center of gravity must be positioned with extraordinary precision relative to the aerodynamic center of the wing. Sweep the wing back as the Hortons did, creating that distinctive arrowhead profile, and you gain some natural pitch stability. But not enough. Not in turbulent air. Not during aggressive maneuvering. The Horton brothers solved this, imperfectly, through a combination of wing sweep, carefully designed wing twist, what aerodynamicists call washout, and drag rudders embedded in the trailing edge of the wingtips rather than a vertical tail. The control system was innovative, but it demanded extraordinary pilot skill and sensitivity. There was no margin for imprecision. The aircraft would tolerate errors that conventional fighters would forgive, but only barely. In 1944 terms, with pilots averaging fewer hours in the air than ever before, this was not a small problem. And yet the performance potential was staggering. With two Junkers Umo 4B turbojets, the same engines powering the Messerschmitt Me 262, the Ho-229 was theoretically capable of exceeding 900 km per hour. Its wing loading was efficient enough to make it more maneuverable than its raw speed suggested. And there was something else, something that only became apparent decades later, when engineers with entirely different tools looked back at what the Horton brothers had inadvertently created. The Ho-229's airframe was not made of aluminum like most German combat aircraft of the era. It was built from a composite sandwich, 2 layers of thin plywood panels bonded over a welded steel tube framework, with the cavity between them filled with a mixture of sawdust and carbon, specifically charcoal dust mixed into the adhesive resin used to bond the outer skins. The Hortons later claimed this was primarily a structural and weight-saving decision. Plywood was available when aluminum was not. The adhesive mixture gave the panels additional rigidity. There was no particular intent, they insisted, to make the aircraft radar invisible. And here is where history becomes genuinely complicated. In 1950, radar wavelengths were long meter-band systems that struggled to resolve small targets at high speeds. But by the time the Ho-229 was being designed, shorter wavelength centimetric radar was in rapid development, particularly in Britain. The question that researchers have returned to repeatedly is whether the carbon-impregnated plywood composite had any meaningful radar-absorbing effect at the wavelengths the Allied chain of detection systems were operating on. In 2008, Northrop Grumman, the company that builds the B-2 Spirit stealth bomber, was contracted to conduct a detailed analysis of the surviving Ho-229 airframe held at the National Air and Space Museum's storage facility in Suitland, Maryland. Their findings were carefully worded. The carbon content in the wood composite, they concluded, would have had a meaningful effect on radar cross-section, but only at specific wavelengths. At the band most relevant to early warning systems the Allied forces were deploying in 1944 and 1945, the absorption effect would have been modest, not transformative. Not stealth in any modern sense of the word, but, and this is where the nuance matters combined with the aircraft's geometry, the story changes. The Ho-229's flying wing profile presented no vertical surfaces to reflect radar energy. No tail, no fuselage flanks, no engine nacelles extending above the wing line. At the aspect angles from which ground-based radar would most likely have detected an inbound aircraft head-on, its radar cross-section was dramatically smaller than any conventional aircraft of its era. How much smaller? Estimates vary, but some analyses suggest that at head-on aspect and relevant wavelengths, the Ho-229 might have appeared as a target, roughly a fifth or even a tenth the size of a conventionally designed aircraft of comparable dimensions. Whether Raymar Horton understood this fully is disputed. Whether he intended it or stumbled upon it, that question does not have a clean answer. But the capability was there, buried in the geometry, hidden in the glue. If you were an Allied commander in early 1945 and you watched this aircraft taxi to a runway, a shape unlike anything in any recognition manual, no propellers, no tail, faster than anything you had ever scrambled against, would you dismiss it as a prototype too strange to be real, or would you treat it as the most dangerous thing you had ever seen? The question is not hypothetical. Allied intelligence officers did see it, and their reaction tells you something important about how the war might have unfolded differently. The V-1 prototype, the first Ho-229 airframe built to powered flight specifications, never flew under its own power. But the V-2 was a different matter. In February 1945, at Oranienburg airfield north of Berlin, the Ho-229 V-2 climbed into the air for the first time under jet power. The pilot was Erwin Ziller, an experienced Luftwaffe test aviator who understood, better than most, what he was strapping himself into. The Jumo 4B turbojets roared, and the aircraft became airborne, and for approximately 30 minutes, something that should not have existed flew over Germany. Witnesses on the ground later described it as unlike anything they had seen. No propellers, almost no noise from the direction of flight, just a shape sliding across the winter sky with impossible smoothness. Then the second flight. The Jumo 4B was not a reliable engine. It was a first-generation turbojet designed and built under wartime production constraints, using substitute materials because the high-temperature alloys available in Germany were inferior to what British and American engineers were working with. Its compressor blades were prone to erosion. Its combustors ran hot and inconsistently, and it had a particular dangerous tendency. Under certain throttle conditions, it could flame out. Unexpectedly, without warning, on February 18, 1945, during what should have been a routine test flight, one of the V2's Jumo 4Bs flamed out during a low-altitude pass over the airfield. The sequence that followed has been reconstructed from accounts and wreckage analysis. The aircraft entered an asymmetric thrust condition, one engine running, one dead. In a conventional aircraft, this is a survivable emergency, manageable with rudder. In a flying wing with drag rudders and no vertical tail, asymmetric thrust at low altitude and high speed was something close to unsurvivable. The Ho 229 V2 struck the ground. Ziller was killed. The wreckage burned, and Germany was running out of time to build another one. In the final weeks of the European War, Allied forces moved faster than German engineers could relocate their most sensitive programs. The American Third Army reached Friedrichroda in Thuringia in April 1945, and there, in a factory complex built into the hills, they found something that changed the complexion of several classified intelligence assessments. The partially completed Ho 229 V3 airframe, along with engineering documentation, jigs, and enough physical evidence to reconstruct what the aircraft was and what it was capable of. This was not an isolated discovery. It was part of a systematic Allied effort, eventually formalized as Operation Paperclip, to capture not just German weapons, but German knowledge. Engineers, scientists, designers, the rocket teams at Peenemünde, the aerodynamicists at Göttingen, and the accumulated design philosophy of a program that had been, in its own chaotic, war-compressed way, 2 decades ahead of the aerospace mainstream. The Ho 229 V3 was carefully loaded and shipped to the United States, where it ended up at Wright-Patterson Air Force Base, Ohio. American engineers disassembled it, measured it, analyzed the composite materials, and filed reports. Those reports went into a classification system from which they did not emerge for decades. The surviving airframe itself eventually made its way to the Smithsonian Institution, where it still sits today, in a storage facility in Suitland, Maryland, not on public display, not quite forgotten, but not quite remembered either. If hidden military projects and declassified weapons programs fascinate you, subscribe to Steel and Strategy, because some of history's most dangerous ideas were never meant to be remembered. For 30 years after the war, the flying wing was considered a dead end. A wartime curiosity. An interesting failure. Jack Northrop did not agree. Northrop, the American aviation pioneer who had been obsessed with flying wing designs since the 1940s, built a series of propeller-driven flying wings in the post-war years, the XB-35 and the jet-powered YB-49, that were technically impressive but operationally troubled by the same stability problems that had plagued the Horton brothers. The Air Force cancelled both programs in 1949, in a decision Northrop believed until his death was motivated by politics as much as performance. He may not have been entirely wrong, but the physics that made the flying wing difficult to control in 1945 and 1949 had not changed by the 1970s. The problem had always been the same. A flying wing is aerodynamically unstable in ways that a human pilot cannot manage alone. The corrections required are too fast, too continuous, too fine-grained for human reflexes. What changed in the 1970s was the computer. Fly-by-wire flight control systems, where a digital computer interprets pilot inputs and makes hundreds of micro-corrections per second to keep an inherently unstable airframe in controlled flight, transformed what was aerodynamically possible. Aircraft that would have been uncontrollable in the 1940s became manageable and then masterful when a computer was placed between pilot intention and control surface movement. The B-2 Spirit, which first flew in 1989 and entered service in 1997, represents the full realization of everything the flying wing promised. Its planform, that distinctive, unbroken wing curve with no tail, no vertical surfaces, no fuselage interrupting the lift-generating surface, is the direct descendant of the aerodynamic philosophy that Raymar Horton sketched out in the 1930s. Whether it descended through direct study of HO 229 documentation, captured in 1945, or through the parallel evolution of engineers working from the same underlying physics, is a question that Northrop Grumman's historians have been careful not to answer too definitively. But look at the two aircraft from above, the B-2 and the HO 229. The shapes are not identical. The proportions are different, the technology separated by half a century. But the philosophical DNA is unmistakable. Both aircraft said the same thing. The conventional aeroplane is a compromise. The wing is the aeroplane. Everything else is weight. The Horton brothers did not profit from any of this. Raymar spent the post-war decades in Argentina, building gliders, occasionally giving interviews, arguing that the whole 229 had been misunderstood and underestimated. Walter died in 1998. Raymar lived until 1994. Neither saw the B-2 enter service, neither received credit, official or otherwise, from any government that had studied their work. The HO 229 itself sits in that Maryland storage facility, one of the most consequential aircraft ever built, measured not by what it accomplished, but by what it foretold. Its plywood composite panels have dried and separated slightly with age. The welded steel framework beneath shows the oxidation of 8 decades. The instruments are missing. The engines are long gone. But the geometry remains. That clean, swept, uncompromising geometry that said, in 1944, what the aerospace industry did not fully accept until the 1980s. Here is what you should take away from this story, not as sensation, but as fact. The HO 229 was not, in any operational sense, a stealth aircraft. It never carried a weapon in anger. Its single-powered flight prototype flew for fewer than 4 hours before being destroyed. The program was cancelled by the collapse of the Third Reich before it could produce a single combat-ready machine. The radar-absorbing properties of its composite panels, while real in some measurable degree, were almost certainly unintentional, and the aerodynamic control challenges it presented were, in 1945, at the very edge of what pilots could manage. But set all of that aside and look at what the Horton brothers actually understood, what they grasped intuitively, without computers, without stealth physics, without fly-by-wire, and the picture shifts. They understood that drag is the enemy of speed and range, and that the conventional aeroplane's shape was an exercise in managed compromise rather than aerodynamic truth. They understood that a wing, a single, clean, continuous lifting surface, was fundamentally more efficient than any configuration built around a tube with wings attached to its sides. And they understood, perhaps without fully realizing it, that a shape with no vertical surfaces and a radar-absorbing composite construction would be harder to see than anything else in the sky. They were wrong about a great many things. The control system was inadequate, the engines were unreliable, the pilot training pipeline was broken, the war was already over in all but name, and the 3x1000 demand that birthed the project was, like most of what Göring demanded in those final years, a fantasy dressed in the language of urgency. But they were right about the shape. They were 60 years early, and they were right. The B-2 Spirit costs more than $2 billion per aircraft. It is the most expensive weapon system ever built. It is also, in its fundamental aerodynamic philosophy, its faith in the wing as an end in itself, the machine that two brothers, with a drafting table and an obsession, sketched into existence in a requisitioned German factory, while the war burned around them. History does not often reward the right idea at the wrong time. The Horten brothers did not survive to see their concept vindicated. The Ho-229 did not survive to fly a single combat mission. But the shape survived. It always survives. And somewhere tonight, a B-2 is crossing an ocean in the dark. No vertical tail, no fuselage, nothing but wing carrying the ghost of a 1944 drawing table inside its composite skin. If you want more untold stories like this, subscribe to Steel and Strategy. Drop your thoughts in the comments and tell us what topic we should uncover next. Your support helps bring hidden history to light.